Hey robot makers, hope you're having a good day so far. So do you want to build a custom PCB for a DIY robot and have a follow-up from the previous session where we actually designed this? Then this is the show for you. Let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, let me get over to our keynote. We can make a bit of a start. So yes, I'm going to cover a couple of the mistakes I made when we designed this. I knew there would be some, but you never know what they are until you get the thing back. That's the part of the frustration with these designs, but we live and learn. So yes, today's sponsor is the manufacturer of all these PCBs that I have here. So each one of these PCBs, including the new BurgerBot one, are all manufactured. Let me get the other one as well. These are all manufactured by PCBWay. So this is the gamepad that we designed as a remote control, a Bluetooth remote control for our robot. This is the little servo helper. So this has a, is it 12 or 16? 12 little header pin things there. You can put power in and you can simply just connect the pins there to get the signal to them, and it'll sort out all the power. It's a problem that I had many times with many projects, so I thought I'd solve that once and for all. Then there's these little Pico Tamagotchi. So this is a little Raspberry Pi Pico powered Tamagotchi type toy. So there's the built version. It's got a little screen on it. It's got 3 little user buttons and the Pico 2 in that case on the back. And then today we have the BurgerBot. So I'll be showing you a little bit more about that a little bit later on. But yes, we did cover the entire from scratch build process on not last week's but one show. So thank you to PCBWay for sponsoring that particular show and today's show as well. Okay, so yes, the custom PCB that we designed 2 weeks ago, they've now arrived. I've got 5 of them in the post, and you can see that the idea is to make the original BurgerBot into kind of a kit kind of form. So rather than relying on some very bespoke electronics from Pimroni, we want to try and simplify this a little bit. So the PCB simply has all the right traces and connections, so we can simply just drop in a Raspberry Pi Pico, a couple of other components, some motors, a motor driver, and the rangefinder. You can see there I've got this little, what I've not soldered up yet. We've got the rangefinder, I've got the Pico there, and it simply just drops in to all those different pins that are on there. Easy to do, there we go, and then push in, and we just need to go and solder them on the back there. We also want to have on this particular project a little battery pack, so I've got a little AA battery pack. This one takes 4 AA batteries, so each one of these is 1.5 volts, so that's about 6 volts in total, maybe slightly over if they're all fully powered, kind of out the box. But we can plug that directly into the Raspberry Pi Pico through its VSys port, and the little regulator will just chop off any additional voltage there. I've tried it and it works okay. Then we've got the motors, so I'm using these little N20 motors. They go by various different names, but if you search for N20 you'll find these. I think these are 150 RPM, and I've also soldered to these some little wires. I'll show you another bit of a problem I've got with these ones. I have put too thick wire on them, but I'll show you that when we get to the mistakes bit a little bit later on. There's also the motor driver, so this is a little board MX1508 I think it's called. So you can see those. These are very cheap online, and it allows you to control 2 motors such as those I've just shown you from 4 pins on the Raspberry Pi. I've also included a servo header on this one, so like the original or version 2 BurgerBot, which has a little servo on it for raising and lowering the pen, I wanted to include somewhere for that to be powered as well. The original one wouldn't work with the servo if it was on battery power. It would only work if you plugged in power to the USB connector. And that was a bit of a mistake in the original design there. And yes, the ultrasonic rangefinder, that will allow us to get a measurement of distance in front of the robot, and that simply just pushes into the 4 pins that we've aligned on the very top of the design there. There we go. It's a bit fiddly to do this while there we go. While the pins are all slightly bent. Well, that one is quite robust. The Pico will fall out, however, if I tip that upside down. It decides now not to do that, of course, now that I want it to actually tip out. So all the different components, it's quite straightforward as a layout. We've got the battery that's providing power to the VSys pin on the Raspberry Pi Pico, and then each of the different components will be wired up by one of those little pathways to the correct component. So motor A and B, connected to the motor driver. The motor driver then has 4 pins which are connecting to the Pico, and the ultrasonic rangefinder, that requires a voltage, a 3 volt and a ground. They're also being routed to the Raspberry Pi Pico's 3.3 volt output, and the echo and the trigger pin are also connected to the Pico. And the server header, the voltage is coming from the full battery power, so that's getting like the 6 volts or whatever it will be, and then the signal pin gets routed to, I think it's pin 0 on the Pico. So we'll have a look at what the pinouts are on this in a couple of seconds time, and you can see there, this is the evolution of BurgerBots. The very first one had the Pico on top, and because it was the original Pico, it didn't have any kind of Bluetooth or wireless connectivity. It was simply just write a program and it'll perform that program. But the actual design of BurgerBot hasn't changed too dramatically. It's a simple kind of circular shape with a bit of a cutout for the wheels to go in. So there's like a little tab there that means that the motor can sort of be attached to the back, and then there's some little 3D printed parts that hold the motors in place, and the rest of the original design is 3D printed. So I thought with this one, let's see how much we can actually attach to the PCB without having to 3D print pieces. So it's kind of a minimal 3D print on version 3. Version 2 included some extra upgrades, and we'll talk about that in a second. So yeah, version 1 had the Pico on top, no Bluetooth or Wi-Fi, and it's kind of basic movement and control. So there wasn't an awful lot that you could do with that. You'd have to basically just program it in there and then let it go. But it did have the rangefinder on there as well. The version 2 has the Pico-W attached, so we can now swap that out with a Pico-2W. And that means that we can have Bluetooth and Wi-Fi control, and in fact that's why I designed that other PCB, which is the gamepad. This is the gamepad version 2. That's got a little screen on it there, so we can display like a bit of a menu. But that simply has on the back a Pico-W. So we can connect to that through Bluetooth, and that means that we can very quickly pair up and have these kind of pre-paired. So as long as you provide power, they'll just find each other, and then you can use the buttons on the gamepad to control the robot. This one also has the pen mechanism, so it moves the servo up and down to make the pen go up or down. And the idea is you could draw things with this. You could essentially create like logo type programs where it'll move around a piece of paper like a turtle. If you understand what I'm coming from, if you don't, these are very random words. So there used to be a little robot back in the 80s, and they called it a turtle, and it worked with the BBC computer, and you could make this little turtle move backwards, forwards, turn left and right, and it was basically the same kind of design as the BurgerBot. Very, very simple, and it had a pen in the very middle, and you can make this pen draw things out. It's kind of like a crude plotter. As long as the wheels didn't slip, it would be fine. This one also includes a Wi-Fi hotspot feature. This is when the Pico-W came out, and there's lots of people looking to see what they could do with Wi-Fi and kind of hosting a hotspot. So you can connect to this robot through Wi-Fi, and you've got a full web interface. You can move it backwards and forwards, left and right, and so on. So there is a full web user interface for that particular robot. I've not really touched that since I originally looked at it. So let's give it a second for that to catch up. So next up, I'm just looking at my broadband connection there, which has dropped right down for a second. I'm not sure what's going on there. I'll just give it a moment to catch up. That's really frustrating. Just wait for that to catch up. I'm not sure why it's dropped so dramatically there. There we go, it's picking back up again. Just had a bit of a momentary glitch there. I think it looks like it's reconnected, and everything looks like it's moving along now. That's good. Thought it was the issue that we used to have back in the stream back in the day, where we'd get these random dropouts and the show would stop working entirely, which hasn't happened, so sorry about that. Okay, so version 3, this is the Pico 2 or Pico-2W based robot. It's built around a custom PCB, so we designed this, like I said, 2 shows ago, so definitely check that out. I'll definitely link that to this main video so you can find that as well. And you can see I've got the actual PCB in my hand here. So this is based on that MX1508 motor driver, so that'll simply connect all the different pins up and to the motors through the roots, and we just need to connect the motors to these little pins here. And there's even space for a battery box as well on here, so we can provide the power, everything that we need, in a nice simple form factor. So if you like what I do and you want me to make more of these kinds of videos, then definitely give this video a like. drop me a comment. Let me know if there's a particular robot that you would like to build. Let me know what that is, and I'll see if I can also do a show around that as well. And if you've not subscribed to the channel, please consider subscribing. It means an awful lot to me, and it really does help the channel grow. Okay, I do go live as well every single Sunday at 7 o'clock GMT, so definitely try and check out if you can on the live stream, and we can have a bit of a hangout after the main show is over. Okay, so the custom PCB, this is a screen grab of the circuit diagram that we created in the show previously. So you can see there's kind of a motors area which has motor A, motor B, and we have all the wires that connect up to that on the circuit board. And then there's also these IN 1, 2, 3 and 4, which is how we control those motors through that H-bridge motor driver. On the bottom left we've got the power, so this is simply providing 5 volts and also 3.3 volts. So on the Raspberry Pi Pico, have I got one of those to hand? Probably have. There is a little voltage regulator on there. Let me just grab one of these out of this little pack. Break into these. So if we look at the very top right hand side of the board there, that's the voltage regulator, and that provides 3.3 volts to the Raspberry Pi Pico, because that's really what we need for this microcontroller. And they expose that on the 5th pin down on the right hand side there. I think it might be pin 39 perhaps. In fact, does it say there's pin oops, it is pin 29, 30, pin 30, there we go. That provides the 3.3 volts out, so we can have that down here in our little power area. Then the rangefinder group, this is where we put our ultrasonic rangefinder. It just requires a echo and a trigger pin. So the echo pin will sound out, it'll fire out an ultrasonic pulse, and then the trigger pin waits for that to come back, hit an object, and it can count we can use that to sort of count the difference between the two sending and the receiving, and that will give us the distance times 2, because it has to hit the object and come back, and we can use that in our code to work out what's in front of it. The servo group, this is for the servo header, so we simply just need the full VCC, that the 6 volts that's coming in. We need the servo pin, which is just the signal pin. That's what we're going to use for the PWM control what angle the servo's at. We also need that ground pin. And then on the right hand side we have the Raspberry Pi Pico-W. It can be used with any Pico, to be fair, but Pico 2W is probably the one that we would use for a lot of these projects going on. And you can see there, GPIO 0 is the servo pin, IN 1 to 4 are then pins 1 to 4. The echo and the trigger are on pins GP5 and GP6. And then the rest of them are unpopulated. So we could add a lot more features to this if we want to in the future. I did consider having some kind of encoder for the motors, so we could actually count how many times the motors have spun round, the wheels have spun round, and count them. But I've not included that on this particular build, but we could certainly do that for a future one. Okay. So pinouts, this is the pinouts I've just read out there just as a little table. So you can see there GPIO 0 is the servo pin, 1 to 4 is the motor controls for motor 1 and motor 2, and that controls the pulse width modulation as well as the speed. And then we have the echo and the trigger for the ultrasonic rangefinder for measuring that distance. So yes, the best day when things arrive from PCBWay. So we've got the custom PCBs which have arrived. Time to check for any issues, and I've got 5 of these in total. So I've just been, I think I've used 2 of them just on my desk there, and these are the other 3. So I'll give you a bit of a close-up of these on the overhead camera. Let's have a look and see what they look like. So this is the top side. So you can see that we've got the ground, echo, trigger and 3 volts. We've got the rangefinder. Then there's a little rectangular box with loads of different holes in it. That's for the motor driver. Then motor A and motor B. I didn't rename them, so they've still got the underscore between motor A and motor B, but that's okay. We've got the holes pre-drilled in it as well, which is pretty cool. So they're just 3M holes, 3mm holes. Then we've got the Pico just here. That's got all the correct pinout information on it, as well as this little indication here, which is how we know which way round to put our Pico in. So if I just drop that Pico in there, for example, you can see all the pin holes are correctly drilled, because we can easily drop that in there, no problem. We've also got the servo header there and the battery connector there as well. So that's what the PCB looks like, and it's got all the nice I think it's about 1.6 millimeters thick, something like that. We can check that. Let's get our digital calipers. 1.5, so yeah, I think 1.6 is what they say on the website, but it's certainly quite solid. It feels like we can definitely use that as the base for our robot. So I'll just put that to one side. Let's get back to our keynote. So time to look at what issues there might be. So what I normally do with the PCBs when they arrive is I do what I call a dry fit. So you can see that I've got the ultrasonic rangefinder. Let's plug that one in there. One of the pins is a little bit tight. That's good because it means it sort of stays in. If I turn this upside down, I can then put the Pico in. And at this point I could plug in a USB cable and check, is the rangefinder working? Before you even solder it, I can probably check that that's working all right. I might just need to sort of angle the pins ever so slightly just so that they're all making contact with the metal things. Once I'm happy that all the parts are correct, I will then start soldering this in place. And it's at this point I noticed that there's potentially an issue with our little motor driver. So if you remember when I put this together, the 3D model didn't look right on top of the PCB. And it turns out that is actually correct. This motor driver isn't actually correct for this. Let me just take these out and show you. So if I go full screen on here for a second, I grab the motor driver and just put it down here so you can kind of see. Look where the plus and the minus are. When I move them to the top there, try and do this, they look correct. So they're ever so slightly off. If I cover them up like so, oops, I'm trying to do this, it's kind of reversed. You can see that there's daylight through there, but they're ever so slightly out. But then worse than that is the other ones don't line up at all. So you can see there's a row there and a row there, and they're not lining up at all. So one of them will, I think we get about 2 or 3. If I try and do that daylight check again to see how we get in light through the back of there, you can't solder that. You can't just drop this onto some header pins and it all aligns. So I'm gonna have to rework that component, and that's a bit frustrating because that meant that the robot doesn't work first time off. But what we can do is we can just hand wire these and get around that. So that's the first thing I want to look at. That's the major issue that's with this. So assembling the robot together, we've got a whole bunch of different components. So I've got some of these moon buggy wheels. These are from Pimoroni. So these are very simple kind of, they look kind of 3D printed, but they're actually not. Let me just take these out. So they've got a nice rubber tyre on them. So these are the moon buggy wheels. You've got this kind of transparent bit, and there's a nice plastic bit in the middle, and then you get this little pack which has, it's got some screws in it. The idea is you can screw these pieces into place. There's this little piece here, it pushes into there, and then what we've then got is a little D-shaped hole. Probably just about see the D shape. If I do that, the flat bit is on the bottom now, and if I get a motor, we can push that motor in place. I've got the things correctly aligned. Do it like that. There we go. So they can just connect up to the motors, nice and simply. So that's how we can control these wheels. We've then got the motors themselves. Let me just jump back one. Sorry about that. We then got the motors themselves. Now these sit in a little 3D printed enclosure. I can probably show you this if I just hold up this robot, which is plugged in at the moment. You can see these red pieces. They're the 3D printed motor holders, and they're simply screwed in place by a couple of M3 screws, and then underneath we've got this other piece. This is I call it a fixed caster because we don't have casters on these robots. You can see there, it just stops the robot from sort of tipping over if I hold it like this. So those two little studs there, they just stop the robot from tipping over. And it kind of does the job of a caster wheel, but we don't need that because this robot's so light. So the motors then, they will then connect up to, just see that little wheel spinning around there, these little header pins. So if I just push that in place there, these are just like regular header pins, and I've just soldered one for each side. Okay, let me just put that down. I'm just going to disconnect that a second. There we go. And what else have we got? The Pico that drops in, solders in place, and then the idea is the motor driver, we would put some header pins on there and it would just sort of slot over the top of that, and then we could solder all that in place as well. The ultrasonic rangefinder on the front, that also has been soldered in place. I think I showed that a second ago. So we can simply just align that. What's nice on here is we actually have, on both the front and the back, it actually has the, you can just about see there, it says voltage, trigger, echo and ground. And on our PCB we have the same things as well, so we can simply just push that in place and then solder them. Just solder underneath, and then we've got our ultrasonic rangefinder in the right place. So we'll test that in a second, that actually all works as we expected, but that's how we assemble the robot. Pretty straightforward. So these fixed casters, this is a new design. The original one, it was just part of the 3D printed base, so I've had to print something that we can then attach to the bottom of the robot, because otherwise the robot would just tip over quite dramatically, as it would sort of slam around and it wouldn't really work very well. So these fixed casters work quite well. You can see there, the bottom right, that's how it kind of looks on the robot. And one of the issues I had with this when I very first printed this one out was that because we've dropped, let's do that again on this one, because I've dropped in some components which have through the hole pins on them, you might be able to see, if I just hold up there, the pins are sticking through the PCB. So when I designed that caster, I'd not thought about that. But as it happens, it doesn't really matter too much, because you can just leave a bit of a gap and screw them right up against the pins. You can probably just about make out that just there. So that actually works fine, not a problem. And yeah, the original caster that I printed out was a bit too short, so it tipped quite a bit more. But with the pins, having that flush up against the pins, it's actually the correct height, so it works out just fine. So they worked out quite okay as it happened. So yes, this is the main issue with this particular PCB design, is that motor driver board, the pins are the wrong size. They're not in the right location. So the right number, the right electrical connection, it's just the actual spacing of them is incorrect. I think this is a fault of the PCB library component. If I design that myself, then I've only got myself to blame for that one. But this is one of the issues about trusting components. So in fact, one of the things I came up against when I was designing these little PCBs, this one is for that Pico Tamachibi one. Let me just show you that. This has a little screen, and it's a very simple screen, a bit like that rangefinder. You can see there it's got ground voltage, SCL and SDA, and that's for the data and the clock for an I2C display. And on some of them, the voltage and the ground are reversed. Why would they do that? Why would they not just settle on one particular orientation? And that means, obviously, if you solder that screen in and it's got the different type, it's just going to burn out immediately. I did have that happen. So I had to I had to change that round and get more manufactured, so that all the screens that I purchased, I bought about 10 to 20 screens. So these are the things we have to watch out for with using PCB library components. So I'll have to carefully measure them with my calipers. I've got some digital calipers, so I'm just going to measure all the holes very, very carefully with this, and then reconstruct that. I might even laser cut out. What you can do in Fusion 360 is save a sketch as a DXF file, and then you can then laser print that DXF file, and then basically just check to see, does that work? Does that look like it's the correct fit? And if it is, we can then get that manufactured. And if not, we can go back and tweak things, because it's very quick to laser cut things. So I have proven that all the routes work properly. So with this robot that I've wired up, I've basically just had to hand wire each of the components to the driver board, which kind of looks a bit messy. Let me show you that on the overhead. But that does actually prove that all the routes work properly, all the electronics are wired up. But we can prove that in a second with some code testing. So we'll definitely do that in a minute. But this is all part of the learning process with PCB manufacture. It's just one of those things that we have to go through and allow a bit of extra time for this. The more experienced you are, I think the more you'll probably get that right first time. Some of the little things I think were that we could improve on this. So let me find that board here. This one, this is the gamepad board, and I just want to show you there. See where it says VCC and ground on that little box? It's really clear which one is the positive and which one is the negative. And I didn't include that because I think I did it during the live stream on the BurgerBot one. So we can actually trace them. So there we go. Battery just has, you can see that there's actually a trace there that's going to the very bottom pin there. And that's the positive. So that tells me that one on the left hand side there, as we look at it in this orientation, is the plus. But it'd be much better if we actually had that on the silk screen. So that's definitely something I want to include in the next iteration of this. The other thing was the motors as well. So I've currently got the motors plugged in via, I'll show you this, a little DuPont cable. Let's go on the overhead and show you that. It's got these little DuPont cables. I'll show you that just there. And we just plug in the cable like that to make the connection. But they're not very great connections. They're quite wobbly. I've had to sort of bend the pins apart to try and get them to stick a bit better. And I don't think these are a great electrical connection. They will wobble about quite a bit. So I'm thinking about what would be a better method than that. So one of the better methods would be to have a screw terminal. I do have a box of little green screw terminal components. The spacing is different. It's more like the servo header pin, but with a missing middle pin. So I might just add an option on the board for that, so we can wire in the motors in that orientation, in that way instead. What else have we got on here? The battery power. Yeah, so that hasn't got the, when we're plugging in the power to the battery, like I said, we've not got that little plus symbol. So a couple of different things there, different types of connectors. I have previously connected with JST, who do the JST connectors. They've got a UK Twitter account or whatever that they reached out and said, like, do you need anything, let us know. So I might get like a catalogue of parts from them and try out lots of different types of connector, because they're going to give a much better fit, a much more reliable electrical connection. So that's something for us to try. So let's test out a couple of parts of this robot to see, does it actually work. So we can test out the rangefinder, the motor, the BurgerBot library that I've built that will wrap all those different parts together, and also that the battery, it works on a battery. So let's give that a try. It's going to be a bit tricky to do this live, but let's give that a go. I always like these things to see if we can actually do it. Okay, so let me bring up a Thonny, and then we can get on with testing this. So I've got over here a whole bunch of test programs: test Bluetooth, BurgerBot 3, button, line, motor, rangefinder. So we're going to be looking at the rangefinder one today, and also the motors and the BurgerBot 3 library. So the first thing we're going to do is let's just have a look at this rangefinder code. So let me just find that on here. So it's simply just called rangefinder.py. And let's have a see what this actually does. I'm going to plug in the robot, and it's probably going to try and run off the desk when I do this, simply because there's a little program that fires up when it starts, and it wants to try and run that. So I'm just going to click stop there. There we go. So it's now not going to do that. So this rangefinder class, let's have a look at this. So this is in MicroPython. I'm importing machine and pin. So the pin will help us connect up the echo and the trigger pins. And we've also got some time things here, time US and sleep US as well. So this class wraps all the variables and all the functions together in a nice object that we can just create an instance of in our code later on. So this initialization piece will take in a trigger pin and an echo pin, because we might want to change that in different designs, so I'm not hard coding anything in there. And we basically just take whatever is being provided, we're setting that to self.trigger. So that's a variable that's within this class. Same with echo. The next one is what we call a property. It's got this property decorator on the top, and that means we can have two functions with the same name. We can have a setter and a getter, or we could just have the getter function. So the getter function will get a value and it will return it back. So because we've done this as a property, we don't need to have the brackets, the round brackets, whenever we use this in our code. We can simply just have like rangefinder.distance, and that will run this function, and it will return the distance in centimeters. So let's have a look how this actually works. So signal on and signal off are going to be equal to 0. We're going to reset the trigger. So the trigger is the thing that's waiting for the sound wave to come back. So we're going to make sure that's low. We have to make it low for a couple of microseconds. So we've got 2 there. And then we can do the actual thing where we're going to fire off the pulse. So we'll say trigger high and then sleep for 5 milliseconds and then trigger low. And then while we're waiting for that echo to come back, while it's 0, then we're just going to update the signal off time. So we're just collecting the time until that bounce back value is 1. Once it's 1, we can then say signal on is equal to that new time. And then the difference between the two of them is how long it takes for that sound to bounce off an object. So elapsed microseconds is signal on minus signal off. The duration is the elapsed microseconds, which we've got there. And the distance to the object is the elapsed microseconds times 0.343 divided by 2. 0.343 is the speed of sound, and divided by 2, and that's because when we bounce something off, when we send out the signal, it has to bounce off the object and come back. So it's actually twice the distance there and the distance back. So divide it by 2 and we get the distance to the object. And then we can then round up the distance to the object, divide that by 10 to make it so that it's centimetres, not millimetres, and then the 1 is just how many decimal points we want to provide back. So we're going to return back, whenever we call that distance function, the actual distance in centimetres. So our little test program is simply going to import that rangefinder class that we've just created there as rangefinder. Distance equals rangefinder, and then we can pass in trigger 6 and trigger pin 6 and echo pin 5, which is what the pins are on our little BurgerBot PCB. And then we can just do a little loop that says print the distance and then get the distance from distance.distance. I'll call that distance. Maybe we should have called that rangefinder. And then we just sleep for a second. So it's just going to continually check for that. So if I now go to, let me see, is it this one? There we go. We can get our little robot here. Let's make it a bit further back. I'm going to run the code. And you can see the distance is currently 21. So if I put my hand in the way and I move my hand towards this, you can see that's getting lower and lower until I get really, really close to it. And then if I take my hand away, it should jump back to 21. We can try that with a different kind of object. Let's try it with this little PCB thing. I'm just trying to show you that. I just move that towards, you can see there that that's getting really close. I think it works to about this kind of distance. Anything closer, it's gonna get a bit confused. But there we go. So that's working fine. We can detect objects in front of our robot. So that's nice. That means we can use that in our BurgerBot class. So let's check the next thing, which is the motors. So let's stop that code. Let me load up the motors. What I've also done is I've copied this rangefinder to the Pico. So I've right click on that and I've say upload to the Pico. So if I do that, it's going to upload it. Okay. And motors is the next one. So let's have a look at the motor class. So this one is also importing pin. It's also importing pulse width modulation, and that's how we can control these motors. And we're going to take in a number of different pins and things. So motor A and motor B pin, and we're going to set the frequency, the pulse width modulation frequency for each of those. And we have, let me just see this. So pulse width modulation A is from the pulse width modulation library, and then we're passing in the pin which is corresponding to that motor pin that we're passing in there. Now this is for a single motor, so this is like either our left motor or our right motor. We'll have to have two motor instances to be able to control our robot. The speed then is just a value between 0 and 1. I just wanted to have that as a way of representing like 0 to 100%, but just as a very simple number. So we've got a couple of different classes. We've got forwards, backwards, stop, speed, and then we've got a getter and a setter in this instance. We can have a look at that in a second. So to make our robot go forward, we're simply going to say the pulse width modulation of motor of the B pin is going to be the duty of whatever speed we put in there times a byte's worth of information. So that looks a bit weird, and it's because we've got a value between 0 and 1. We have to sort of scale that up to be a full byte in size. And then pulse width modulation A, this is, we have one pin to control the sort of direction of the motor, and one of them to control the speed of the motor. So that's what this reverse pin stopped is all about. And then backwards, we simply just flip round the orientation of that, and it'll spin in the opposite direction, or whatever speed we've currently got that set at. So we need something to be able to stop the motor. If we don't have that, it'll carry on spinning until we pull the power out. So that simply just sets the duty to be 0 on both of them. And then the speed, we're simply going to have a variable that's called underscore speed. It's kind of like a hidden variable just for us to use in our class. And this getting property will just mean that we can say dot speed in our code without the brackets, and it'll return that just by running this code. The setter one will set the speed. So if the value is less than 1 and greater than 0, then it's going to set the speed to be equal to the value. Otherwise, it's going to say the speed must be between 0 and 1. It's just a nice bit of error checking code in there. So that motor code we can use in our robot. So let's just close that and load up our motor test. So we've got two motors, motor 1 and motor 2, and they both require 2 pins each, one for direction and one for speed. I'm going to set the speed to be half, so that's half for both of them. I'm going to start out by stopping both of the motors, just to make sure if they've run a previous code, they're definitely going to stop at this point. And then I've got some code down here, do test. The reason I've got this is if I don't call this, it'll just stop the motors, and if I want to run the test, I'd simply just do test like that. So let's run this code and see what happens. I'm just going to get this over here, and what we will need to do is just make sure that the kind of bug that can occur with this is that the motor pins are not pushed in properly. Let me just do that. If I get a good connection on these, they should be sort of spinning round. They're quite strong, these motors, as well. So you can just see that motor there, that wheel keeps spinning round. And that means it's got like a good electrical connection there. So I'm just going to stop and then run my test code. So what it should do is it should go backwards, stop, forwards, stop, backwards, stop, forwards, stop. So if both of our motors are connected and working properly, we should see that the wheels will actually rotate round. It might be easier for me to show this kind of side on, and we need to have that in a loop as well so that it carries on doing that. Let's do a while true, and let's just tab that out a bit, and it should carry on doing this test now. So let me just save that and run it. Right, so you can see that motor on the left hand side is working. This one seems to have a bit of a dodgy connection to it, and it's simply just going to do the left motor backwards and forwards, and then the right motor backwards and then forwards, and then the left backwards and forwards. So you can see them both working like so. So I'm just going to stop that. And if I run this while it's on the desk, it will try and sort of run off the desk, as you can see, and slam into everything. So it does prove that these are quite strong and working okay. Right, so that's both the rangefinder and the motors. So if we pair the rangefinder with the motors in some code, we can achieve some interesting things. We can make an obstacle avoidance. So if it detects an object within a certain distance in front of it, we can make the robot say stop, turn, and then go forwards, or spin completely round and then go back the way it came, for example. There's lots of different things that we can do with that. So let's have a look at our Burger 3 code. So this BurgerBot version 3. This is a class that we can create to encapsulate both of the motors and the rangefinder and other things as well, like the servo pin for the pen up and pen down. And I've even included an LED just to show that the robot is actually active and working. So if I hold this up, you can see that there's a little LED just lit up just there, a little green LED. And it's just a way of indicating that the code has switched that on. We could make it flash if we wanted to, whatever we want. So in the BurgerBot, we've got left motor and right motor as two variables. They correspond to the motors that we've just created, those motor classes. So pins 1, 2, 3 and 4. They correspond to those IN1, IN2, IN3 and IN4 on our motor driver, which I've now lost that. Let's it was on this desk a second ago and I've now lost it. So wherever that, there it is, that's gone. So yeah, that corresponds on here to those pins on the right hand side there. I think they're upside down, that's why we can't see them very easily. So the iron 1, iron 2, iron 3 and iron 4, and they correspond to motor A and motor B's direction and speed. Then we've got the rangefinder, that's on pin 6 and 5. And then we have the LED, which is the built-in LED. So we don't need to specify what pin that's on. It used to be on pin 25 on the Raspberry Pi Pico, and then they've just made it LED, so you can it'll understand which pin that refers to, because it's kind of an internal routed pin. Pinned out just means it's an output, because the LED is going to shine output. So we just have to define that, and then we can just say what the initial value of the LED is. So LED.value 1 will set that LED to be on. So then in our BurgerBot, we've got a couple of different things. We've got initialization, so we're just setting the speed of both left and right motors to half. So that was half speed. As you saw it shooting across the desk there, it can go twice as fast as that. We've then got forward and backwards. So because the orientation of both of the motors, they're not both facing in the same direction. They're kind of, one of them is flipped. So that just means that we just need to be cognizant of that when we want the robots to go backwards and forwards. We need to potentially flip one of them. But I think the way I've wired these up, it just happened that they're both correctly wired, so that if you send both motors forwards, you don't need to reverse one of them. That makes sense. If you don't know what I mean, just think about how if you've got a motor spinning in a certain direction and you flip that the other way, it's going to be sort of spinning in the opposite direction. So if you want both of the motors to go forwards, one of them is actually going to have to spin in the opposite direction because it's flipped 180 degrees. So to make the robots go forward, we'd say left motor forward, right motor forward. To make the robot go backwards, we do left motor backwards, right motor backwards. We're not doing this for a duration of time, we're just making it do that until we change that state. Stopping the motors will stop the motors completely. And then we've got turn left, so that's where we need the motors to sort of spin in opposite directions. So to turn left, we need the left motor to go backwards, and we need the right motor to go forwards, and that'll sort of twist the robot and it'll kind of make it spin round like a little tank. And we need to just reverse that to make it spin right. And then we've got two things. We've got follow and avoid. So follow says get the distance from rangefinder.distance. Notice we don't need the brackets at the end because it's got a property. We could treat it like a variable. So distance equals rangefinder.distance. If distance is less than 10 centimeters, stop. Otherwise, go forwards. If the distance is less than 5, then go backwards. So that will go forwards until it finds something. If that thing is actually moving towards it, so it's not like a wall, like an obstacle, but something that's physically moving towards it, it needs to back out because this thing is going to hit it otherwise. Avoid simply just does the kind of like the backing off thing. So distance, we grab that again. If the distance is less than 10, we just get it to turn left. So it'll just turn left slightly, and if there's something there, it'll turn left again, and it'll keep turning left until it can't see an object in front of it, and then it'll just go forwards. So that's our BurgerBot library. That encapsulates everything on this particular PCB-based robot, because I've not got the pen mechanism attached yet, so we've not included any of the pen up, pen down on there. But we could certainly include that in the future. So I've also copied that to the Pico, so you do upload to copy that to the Pico. So they're now all on board the Pico because we need that code to be autonomous when we run it. So what I've then done is I've got a little test program, so I've just called it test BurgerBot version 3, and that's simply this bot equals BurgerBot. So that BurgerBot class we've just created, we stop the motors from running just in case they happen to be running to begin with, and then while true, bot avoid. So the motors are going to spin forward until something is less than, was it 5 or 10 centimeters in front of it, and then it's going to turn left until it has a clear space in front of it. So it should avoid things. We could put this in a maze, and it should be able to find its way around a maze very, very simply. And then while that is true, it's going to do that, otherwise it's going to stop. So we can try running this code and see what happens. It's going to be a bit tricky on this very crowded desk that I have here, but we can certainly give this a go. Let me just move some of these PCBs out the way, so we've got a bit more working space, and then we can give that a go. I've just dropped loads of them on the floor. Right, let me just put these over here. And that and that. Let's also move these motors. Yeah, so what happened with these motors, I had some really nice wire that I'd ordered online, and I've crimped on the little cables so that they can go in these little DuPont connectors, but the cable's too fat, so when you try and push them in, it doesn't actually go in, it just gets stuck, and it doesn't go in the connector properly, which isn't great. So I'm basically just going to have to desolder these to use these two motors. Right, okay, so what I want to do is have some kind of object in front of the robot so that when the object gets to a certain thing, it will spin around, so it should go forward and then try and turn left. That's what should happen in theory. It does require these motors all being electrically connected properly, which can be a bit of an issue on this one. So let's give this a go. I'm going to hit run, and there we go. It's kind of got stuck because it can see the object. You can see that it's avoiding it. This motor here is not quite connected up. That's what's going on there. Let's just plug that in again. So that shaking thing is the rangefinder saying that you're on the cusp of finding something. So as I put that in front of it, it's kind of trying to avoid it. That motor's not behaving properly there, but you can see what's going on there. When I put that right in front of it, it'll spin right round in a circle. Until it finds that again. So you can get a better connection on that. So yeah, this is one of the bit of design flaws with this particular robot. These DuPont connectors are not great. So let's just stop that. Stop. So I've said stop and the motor is still spinning, and that's because if it doesn't catch the stop signal, it'll just carry on spinning. So let's just do that, because it's really just telling them the controller board, there we go, stop. It's telling the controller board to kind of open a gate, open the power to a particular strength using pulse width modulation. So if our code stops, it'll carry on doing that. So there we go, that's a little test of the BurgerBot. Now the real final test is, can we connect our battery box to the robot, and will it be autonomous? So this is going to be a bit fiddly. It's going to carry on running whichever program I've loaded on there. So I think it's the avoid one, and if I remember, it's the red goes to the bottom there. I'll be able to see that it's connected up because there'll be a little LED. I just put it on top of there. Let's see if I can get this to balance and also work okay. It's a bit fiddly to do this. It might just have to drag the power a little bit, I think. Right, there we go. If I put my hand in the way, it's going to try and reverse back. There you go. And you can actually see this is running entirely on its own accord. There we go. If you put something in front of it, it'll stop. Otherwise it'll just keep spinning around in a circle. The reason it's spinning around in a circle is because this motor connector here is not quite connected up nicely. Now of course needs somewhere to put this battery back on the back of it, so that, there we go. There we go. It nearly worked properly then. This is at half speed. There we go. Trying to battle the other BurgerBot there. There we go. And of course we could just pull the power out to stop the robot, because I've not included a power on and off switch. That's probably something else we need to add to the list of things to improve on our PCB. So there you go, we've tested the rangefinder, the motors, the BurgerBot library, which encompasses all those different pieces of code, and also the battery, that we can actually power it by a number of different batteries, 4 AA batteries. I think they're all reasonably full power out of the box. Okay, so if you want to get yourself one of these really cool Robot Maker hats, you can do that by going to kevsrobots.com/merch, and we have loads of those available. You can order one of those in a number of different colours. We've also got the mugs, which are quite cool, and some t-shirts and hoodies as well. If you want to join our Discord community, we have a really active Discord community. Honestly, it's growing every single day. More people are joining that, and you can post pictures of robots that you've created, and pets as well, if you want to sort of show anything to your family pets and whatnot, because it is a nice community on there. We do like cats and dogs and everything else. And yes, if you have a problem with your code, that's the best place to get your code answers, your code resolved. Don't email me directly, because I simply don't have the time to go through every single email that I get in a week about I've got a particular problem, or I'm a student and I would like you to do my code for me. Go to Discord, you probably get all the help you need from there, so definitely check that out. And if you ever want to follow me on social media, I'm on all the social medias. I'm on Kevin McAleer at threads.net. I'm on TikTok at Kevin McAleer 6. I'm on Instagram at Kevin McAleer. I'm currently on X at KevsMac. On Mastodon, I'm at kevsmac at mastodon.social, and I'm also on Blue Sky at kevsmac.bsky.social. And I think definitely Mastodon on Blue Sky are the ones I seem to spend most time on, with a little bit more on Threads and maybe TikTok, a tiny bit of Instagram, not too much Threads nowadays. X nowadays. And if you want to get your name in the end credits, so you can do this by going to kesrobots.com/coffee, and you'll find all the instructions there to either do a super thanks, a super chat. You can join the YouTube membership program, or the Buy Me a Coffee membership program as well, if you don't want to do that way. So, Ford saying, wait, Kevin, have you really had a student write here? I get multiple students many times a month saying that they've got some kind of assignment due in. It's usually like around the time of year when assignments are due in, and they want me to do their entire project for them, it seems. So so yes, let's give a shout out to our supporters. So on the left hand side here we have people who bought me coffee recently. So Marie Louise Mayer bought me 3 coffees. Thank you so much for that. Really do appreciate it, and I'm a big coffee drinker, as you know. Michael Carroll and Edu73 or ECU751 also bought me a coffee as well. And we've got a new member in our Buy Me a Coffee. So Andrew, let me get this correct. So it's Pascavewich. Let me just find that, because he actually went to the trouble of telling me how to pronounce his name. Pascavewich. There you go. Pascavewich. We've got Shemi, we've got Jeff Johnson, Dean Corty, Marlene Brent and Tom. And then over here on the YouTube side, we've got Marie Mayer, we've got Michael Emerson, Steve Phillips Ford, we've got Bello, we've got Orksrad39, Littleback, Paul, Johnny, Handsome Cheerlights, we've got Prem Kumar, we've got Steve Cross, Chompo Jolly, Alice Aware, Cassie, Tinkering Rocks, Johnny, and we have Tom as well. So thank you so much for supporting me and my crazy robot making stuff. I really do appreciate every single one of you. And yes, it's at this point in the video where YouTube will then recommend over here a video for you to watch next, which is from the whole backlog of videos I've created. I spend a lot of time putting these videos together. Each project gets written up on kesrobots.com, so you can check out the build for this particular project. This one is a bit of a different format, in fact, but definitely check that one out. It's got lists of all the videos that you can see on there, and it's over 350 now, I think. Probably getting towards 400 videos, so definitely check that out. And yes, the more that you watch, the more that YouTube will say, Kevin's doing some interesting stuff. Definitely want to check out more videos on that. And it's at this point in the video, if you're watching this on replay, I will say thank you so much for watching, and I shall see you next time.